lecture 49, Statistical Measures of Safety Program Effectiveness, part 3, under module 10, Prescriptive Safety Analytics. There are many statistical measures. We have already discussed some of the measures. Today we discuss two more measures, repeated measures ANOVA and Friedman test. You have already seen this slide, what I said, that there are parametric and non-parametric measures. T-test for paired data ANOVA, these are parametric. Then Wilcoxon rank sum test, Wilcoxon signed rank test for paired data, Friedman test. And we have discussed T-test. Then we have also discussed Wilcoxon signed rank test for paired data. Today we discuss ANOVA, repeated measures ANOVA and Friedman test. So, repeated measures ANOVA is similar to randomized complete block design. Actually, here what we are how we are doing this experiment or the study design, what we have designed the study in such a manner that data will be captured on the same subjects at repeated under repeated treatments. So, that is what the repeated measures, basically here the treatments, you can see the treatments is one important part. So, what is treatment here? Treatment means any safety program or safety program type, its different types. For example, if we talk of safety program is training, then there could be classroom training, there could be on job training, there could be targeted SOP specific training or job specific training. So, three different, that means treatments we can say from training point of view. Now, you think of what is subject here? Subject basically, if in individual goes through these three groups of training method, then actually we can say that the subject is gone under repeated treatments. So, the second one is basically that, suppose in the same way in the last class we have given one example where I said that there are 12 locations, and in each locations the people who are working there, they are giving some kind of training, and before training and after training the safety performance in terms of safe operating procedure violation we compared using T-test and Wilcoxon signed rank sum test. So, in the same manner we can say, suppose if we select suppose R number of that means locations where everywhere suppose there are some number of people there. So, the every location the people are going through these different types of treatments, and then the issue is that if we want to understand whether the treatments are equally effective or there is a difference, then there is one important issue is that the subjects are basically different. Actually, in order to make it more different, we have taken a group of people from every location, and these locations we considered as basically the subject there, or I can say specifically in under some kind of experimental runs that can be thought of. So, whatever may be the case, please understand that if we consider R number of individuals workers and they will go through different type of treatment, then obviously as the individuals differ, so there will be effect of the subjects or individual also, whether the group of similar individuals or individual as such. Okay. So, so this is what basically we want to test using ANOVA, repeated measures ANOVA, where our null hypothesis is H0, null hypothesis is no difference of means among the treatments. So, we have C number of treatments y1 to yc, this is basically from treatment point of view. We have R number of subjects. Now, the subjects can be individual, subjects can be locations, can be any other entity that you can consider. So, if you collect data under such condition following the approach what we have discussed here, then you will be having this much of data with you. So, what I mean to say that what is the first cell here? First cell is basically talking about the response variable. If it is safety performance, let it be safety performance for the combination of x1 y1, which is nothing but that the subject x1 is exposed to treatment y1. In the same manner it will continue. Okay. Now, after that, if you carefully design the training program, as for example, because I have already given example 3 training program. So, then our C will be 3, C will be 3, this C will be 3. So, 3 treatments. Now, you can find out what could be the R value. It all depends on how you are doing the collecting the data with proper study design. So, essentially our aim is to know whether the 3 training programs is basically giving results or effective or not, or there is no difference. Okay. So, the subjects being different, they also impose some kind of variability in the response variable, here the safety performance. For example, if we consider individual, then the individual A and individual B, even though given the same kind of training, their safety performance may differ because they are different individual, their capability and other things are there. So, that individual brings certain amount of variability into the response variable where it is safety performance. So, you require to block that part of the individual variance, and then only you will be able to find out whether the treatment effects are significantly different or not. So, for that purpose the repeated measures ANOVA is used. ANOVA is analysis of variance. Now, as the subjects bring variability and you require to block it, it is similar to randomized complete block design, which is very popular in experimental design, particularly laboratory based experiments, okay, where you can block the variability by the subject. Other way I can say the subjects or the raw are basically talks about, but they can be talked to as a block. Okay. So, whatever may be the way you define, but here the key issue is that subjects are exposed to different treatments and subjects introduced variability at the same time, but you want to identify the treatment's effect, whether the treatments are really effective or not. So, for that purpose you require to have certain mathematical tools, and that is what we are discussing as repeated measures ANOVA. So, here another important part we are talking about dependent sample. The reason is because the sample R number of subjects, they are exposed to all the treatments. So, that is why if I consider for treatment 1, this R is the sample, treatment 2 are the sample. So, that means the treatment basically it is not basically changing, the subjects are not changing, same subjects are being repeated. So, with this explanation, now with the hypothesis that there is no difference of means as there are c number of treatments. So, we can talk about the mean of first treatment is mu 1, then mean of second treatment is mu 2. So, like this you will be finding mu of c treatment will be mu c. So, this is the null hypothesis. What is the alternate hypothesis? Alternate hypothesis is mu I not equal to mu j for at least one pair, where I and j varies from 1 to c, but obviously I not equal to j. So, this is the hypothesis. Now, after the proper data collection through appropriate study design, you will be getting this table like this. Then you also require to compute some other that quantities, like here row sum, this square term is wrong, it is not correct. So, SR 1, that means sum of row 1, sum of row 2. So, like this also SRR earth row sum. So, similarly column sum means this square term you please erase, this is not correct. Okay. So, SC1 SC2 to SCC. In addition, what you basically compute, you compute also average. So, row average as well as you can compute column average, row average and column average, these things will be required. So, as there are r number of rows, r number of row average and c number of column average, that will be also computed, and then grand average will be another. Grand average means average of all. With this notation, now if we want to know what is the variability accounted for by the treatments, then the formula is this. SS means sum square treatment. So, sum square, that is in one way it is basically measure of variation or variability in the response variable that is taken care of by the, or that is contributed by the treatments. So, here that will be our k equal to 1 to c, because we have c treatments. So, varies from 1 to c, and the column sum is SCK, the kth column sum is SCK, that square. Okay. So, if you want to use square here, then you have to write row sum square, also this is also column sum square. So, that particular square term will come. So, then row sum square, column sum square and the sum of column sum square, that is why SS sum of sum. So, they by divided by r. What is r? How many rows are there? Minus t square by r c, where r and c you understand number of rows is r and number of column is c, but what is your t square? T is nothing but grand total. So, grand total square, that means all x1, xy 1 1, all those response values will be summed up, that is the grand total. So, then obviously, you can understand that you are in a position to compute the sum square variability contributed by the treatments, here the training, different types of training. Okay. So, if different types of training are imparted, so what is the difference in the safety performance of the trainees, and then we want to see whether the difference is there or not. So, in order to understand that, you have to compute certain quantities. First and foremost, I said that the row sum, column sum, then row average, column average, after that SS treatment. Then similarly, as I told that the subjects are also introduced variability in the responses. So, you require to compute the subject contribution. Subject here means it may be individuals in R number of individuals, or maybe R groups, each groups having similar number of each group having some individuals, maybe group of people, but for the same job or the same type of basically profile, job profile or work activities or task activities being done. So, then for SS subject you will find out this, use this formula to find out the contribution of subjects in terms of introducing variability in the safety performance. Then in addition, these two variability, if you add together, they will basically give you the total variability basically. Okay. So, these two variability if you add together gives you total variability. It is not correct. What is correct? Total variability plus error, because there it is not that the overall whatever variability is there, this can be talked about by SS total. Then you can use this formula to compute this. That means for each and individual values you are squaring it and then taking the sum and then minus T square by R C. Now, you know what is T square by R C. So, what we want to basically tell you here, that this total variability in the response is actually attributed to, first is treatment, second one is subject, third one is some random error. So, as a result the sum square total will be equal to sum square treatment plus sum square subject plus sum square error, and using this subtraction formula you can now compute the sum square error. So, as a result I can say that causes of variation or sources of variation, one is treatment, subject, error and total. This you require to compute. Actually, this is example from the classical ANOVA, analysis of variance. All of you might have gone through analysis of variance. Here we are utilizing this in the safety and risk analytics domain, particularly from prescriptive safety point of view, prescriptive safety analytics point of view, so that we can evaluate the effectiveness of certain safety program, here the training program effectiveness. So, this requires some amount of knowledge of analysis of variance, that how the variability are introduced. So, I said that the variability, there will be several sources, then you decompose the total variability, this total variability into the component variability, and in the computation you know that as per the statistical requirement, the computation particularly imposes certain degrees of freedom, and that means some freedom is available for computing SS treatment, SS subject and SS error. So, that is given in the third column of this table. This is very important. While we are computing the sum square treatments, because there are C number of columns. So, we have used these C column values. So, and ultimately at the same time we are subtracting the total, the T square by R C. So, that particular mathematical issue or the statistical issue, what it is, it's basically making the situation like this, that there will be C minus 1 degrees of freedom for computation of SS treatment. Similarly, R minus 1 degrees of freedom for subject, and R minus 1 C minus into C minus 1 degrees of freedom for error, and for total, because there are R C total observations. So, minus 1 degrees of freedom for the total. This is also very important, and after that what happened in basically this hereditary measures ANOVA, or as such in ANOVA we compute mean square. What is the mean square? Mean square is nothing but sum square divided by its degrees of freedom. So, that means MS treatment is nothing but SS treatment by C minus 1, MS subject is nothing but SS subject by R minus 1, MS error is nothing but SS error by R minus 1 into C minus 1. Here we are interested to basically know whether the treatment effects are significant or not. So, as a result we create it is a parametric one. So, this quantity MS treatment by MS error, MS treatment by MS error, this quantity follows F distribution, F distribution. So, this F distribution you have to check, and if the computed this computed value based on the experimental data, if it is more than the tabulated value, then we reject the null hypothesis. This null hypothesis will be rejected. So, with this background, now I am going to the example. So, again please let me repeat here, the when you are seeing row sum, then the square will not be there, better you will write row sum square and column sum square, that is fine, then things are, this table is okay. But actually you require row sum to compute, row average to compute, as well as row sum square you have seen, that also we have used. So, the decision making is that reject the null hypothesis if the computed F, what you are computing here, if it is greater than tabulated F, and how to get the tabulated F. For the tabulated F, you require to know F table, and in the F table it has 2 degrees of freedom, numerator degrees of freedom C minus 1 here, and denominator degrees of freedom R minus 1 and into C minus 1, because MS treatment, SS treatment has C minus 1 degrees of freedom, SS error has R minus 1. So, this ratio you are making. So, the ratio F has this degrees of freedom. In addition, you will take error that is level of significance. So, using this usually alpha will be 0.05, or you can you just find out for this particular F value what is the probability value. If the probability value is less than 0.05, you can say that yes, there is difference in the treatment means. So, there means effect training the programs are effective. If there is on the other side, we can say it is not effective. So, I am sure that you will be able to do it, and although it's required time, but with an assumption that you are having some background in this particularly T test and ANOVA. So, let us do something more on it and see one example. Here the example is again we are basically saying that let the same example, earlier example, we are just extending it, that there are 12 locations, that in the 12 locations in the plant, each locations let there are some people working. We have taken group of people of similar other characteristics from each location, let it be, but location to location there can be difference. And then what happened, they were basically given to first classroom training, then second after hands-on training and targeted training, something like this, and we are observing the influence of the different trainings. So, under such situation what will happen, you can use the repeated measure ANOVA concept, which is similar, which we have discussed earlier, and you can see the results. Now, see the result, the way result we basically got. This is the data. Now, I say that the sources of variation, we are writing here sources of variation or causes of variation. One is treatment, its sum square using the formula is like this, subject sum square is like this, error sum square like this, and total will be sum of these three. Or other way, you create first total, that is the way formula is given, first create total and then find out the error sum square by subtraction. As there are 3 different treatments, so 2 C minus 1, that 3 minus 1, this degrees of freedom 2, there are 12 subjects or locations. So, 12 minus 1, that is 11, and then you can find out that 11 that what is the total, or I can say that 11 into 2, 11 into 2 will be the, because C minus 1 or minus 1, that will be the error, and the total degree of freedom like this. So, in the same using the procedure, when we compute that the p value is for the treatment effect, p value is 0, 0, which is less than 0.05. So, you can understand the f value is very high. So, null hypothesis is rejected, that there are significant differences among the 3. Instead of population, you can write training program due to the treatment that they are basically, from the data we are finding it, they are improving, and it is logical and it should happen. So, if you are you have any kind of incubation or training center where you are giving different kind of training, then try to collect data, and before that you try to make groups and or the training design methodology of training in such a manner that you will be able to capture data in this format, then you can use this particular technique what I have discussed here. The disadvantage of this repeated measures ANOVA is that is a parametric one, and it requires basically F distribution. You have seen already the F ratio what we have computed, it requires probability distribution, that is F distribution. And in the other hand, also in ANOVA, general ANOVA, we basically consider that the data coming from response variable is normal. So, such probability assumptions most of the times in reality are violated, and you may be interested to go for some kind of non-parametric test, and equal to this repeated measures ANOVA, analogous non-parametric test is Friedman test. So, it is used for dependent variable paired data. So, Friedman test it is similar to analogous to repeated measures ANOVA, and again the paired data case, dependent sample or paired data case, similar to the repeated measures ANOVA what you have seen earlier. So, here what you require to know, then you require to know that what are the computation that is needed. Other things remain same. You have the data collection from the for the example like the training data. Similarly, other treatment data, from data collection point of view, it is fantastic. Same thing you have to do the way earlier I explained, but the computation issues are different. So, being non-parametric, obviously it will be different. So, you know that R number of subject and C number of treatments. Now, what you do, replace the data point in each of R subject with corresponding ranks. Okay, corresponding ranks. That means you just arrange them in ascending order, and then put 1, 2, 3, 4 some like this. So, for each of R subjects, so every row you consider and do it. Then with 1 assigned to the smallest as I told you, and C assigned to the largest value, because there are C different treatments. So, C number of ranks for each of the row or each of the subject you will be getting. Then calculate column wise, because column is treatment, or treatment wise sum of ranks. Here instead of summing the response values like the repeated measures ANOVA, here converting the response values to ranks, and after that you take the sum of ranks. That means column wise sum of ranks for each of the treatment. So, as we are using column wise, so that is why we are using R, this is the rank, dot k, because each of the cell is represented by j k. J stands for column, k stands for row, k equal to 1 to r, j equal to 1 to c. So, column sum, that means it will be summed over r number of rows. So, that is why the dot is put here. So, once you compute this, then the Friedman test statistics is this FR Friedman is 12 by RC C plus 1 k equal to 1 to C r dot square minus 3r into C plus 1. Okay. So, here the test is a little different. Here basically H0 is medians of the populations are all equal, medians. Instead of we are saying C treatment, here basically you can write treatments. So, instead of talking the mean, here you are basically considering the median. Okay. So, then if you compute this FR value follows chi-square distribution with C minus degrees of freedom. Please understand, here also we are using chi-square distribution FR as one probability distribution. Earlier repeated measures also I have used F distribution, but from the assumptions point of view, here no other assumptions, probability assumptions like the response variable is normal or not, those things are not required here, but in the repeated measures ANOVA such probability distributions are required. So, that is basically the difference, and that is why here it is non-parametric, earlier it is parametric, but at the end again here you are using the you are creating a ratio like this one, that some quantity FR, and that FR approximately follows this chi-square distribution C number of degrees of freedom. Another important part here is that as you are for each of the rows or the subject, the C number of response values are ranked. So, 1 to C, 1 to like C ranks are coming, but it may so happen that some of the cases the response value is same. So, their rank will be tied. So, if there are tie cases, so your F ratio, that FR Friedman test statistic, that should be adjusted, and the adjustment formula is like this: FR adjusted equal to FR by C. FR you are computing using this formula, and then where C equal to 1 minus sum of, suppose if we say it is I equal to 1 to let there are m number of ties, then Ti minus Ti cube minus T. You do not know how many ties will be there. So, there could be m number of ties. So, for each of the ties, T stands for ties. So, Ti, that is if I equal to 1, T1 minus T1 by this. So, this will give you then if there are T2 like this, take the sum and you will get the value of C. Once you have the value of C, you are having this value, this one, that FR adjusted value. Now, using with these quantities, you can go for the test that whether the medians are equal or there are difference in medians. Okay. So, that same example we have considered here, and you just see that what we have done basically, that each of the rows, as there are 3 number of training program trainings, and then the rank will be 1, 2, 3. So, that way ranked are computed against each of the rows, and there is one tie, the tie is also broken, and ultimately using R code we found out the values. What are the values? That FR value is this 18.292, C value is 9.979, FR adjusted value using the formula is 18.681, and corresponding p value at 2 degrees of freedom, because C minus 1 degrees of freedom. So, it is 0.001. obviously null hypothesis is rejected. There are significant difference among the 3 treatments or the training program. Okay. So, this is the way you have to evaluate the effectiveness of your program. Obviously, if you do not have right kind of data, you cannot do this, and getting right kind of data is not easy, and as a result what is required, you have to have right kind of methodology, right kind of study, so that you can get the data the way you are basically planning to use. Obviously, if you do not have that particular data set, you cannot go for like this. Okay. So, there are many ways to do. So, some ways we are discussing. If your data is not amenable to that technique, you can use other techniques. Okay. So, another issue we want to discuss here is that okay, as there are 3 different training methods. So, instead of doing this Friedman test or repeated measures ANOVA, can we not test them pair wise, in the sense first training versus second training, second versus third, third versus 1. So, that you can do, you can use non-parametric Wilcoxon signed rank test pairwise one, and then for each of the pair you see that whether they are different or not. So, obviously, the median is different here, because you just see the for all the pairs p value is very low, and from the right hand side the box plot, where basically talking about that the 3 different training levels, first is hands on, classroom, then hands on, then the targeted training. So, obviously, what you are finding out, yes, there is a difference, because the you see that violation wise basically it is reducing. So, first level, then second level and third level, something like this. Okay. So, with this I conclude that there are parametric and non-parametric measures which can help you in evaluating the effectiveness of safety programs. Safety program can be safety training, can be inspection, can be your other kind of programs like audit, whatever you say. You have to first understand that what are the safety programs and how we are collecting the data, and then you choose that which technique will be useful. On the other hand, if you think that some control data can be collected just for the purpose of validating that whether the train or verifying the training is effective or not. So, that type of experimental data also you can collect, and accordingly you have to use the appropriate techniques. I hope that the techniques whatever given so far in this week, the parametric and non-parametric is easy. We have not gone to very difficult techniques, and in the process if you find anywhere there is problem in the concept, or if we have said something wrong, so that you please highlight in the discussion forum. Definitely we will have a good discussion on it. Now, the book is that Hollander et al. Non-parametric statistical methods, and obviously the second one, actually this is our area, we all are working in this area. Okay. Thank you for your kind listening to my lecture.